Welcome to the next video in linear models. This is video 3 where we're going to discuss exercise 1.3 that can be found in chapter 1 section 1 of the textbook. The exercise is to show that the covariance of any random vector y is always a non-negative definite matrix. Let's first recall the definition of what it means for a symmetric matrix, and I'm not going to bother demonstrating that the covariance is a symmetric matrix. I think it should be pretty clear, if not completely trivial, from what we've already said in previous videos, that the covariance matrix is a symmetric matrix. But so again, to give the definition here, a symmetric matrix M is non-negative definite if for every vector that you choose from the space of all vectors R to the n, right? So notice the matching dimensions here. If you take the transpose times the matrix times the vector, and by the way, make sure that you think about the dimensions of the matrices involved here and how matrix multiplication is well defined. And moreover, the result of this is a 1-by-1 matrix, which is to say we just treat that like it is simply a real number. And then we can say that this real number is greater than or equal to 0. This is the condition that defines a non-negative definite matrix. So we're going to try to show that the covariance of a vector y always satisfies this property. Now let's recall what we got from the previous exercise. We showed that for any random vector y and matrix A vector B, that we get this, right? The matrix A and the vector B are constants, but we always get this result. So with these ingredients kind of laid out, we are going to prove that the covariance is a non-negative definite matrix. And so, right, just by definition of what we have to do for that, we will go ahead and set V as any arbitrarily chosen vector from the space of vectors R to the n. And let's try to write down V transpose covariance Y times V, right? Because after all, this is just what we need to show that covariance of Y is non-negative definite. Well, if we just do kind of the most obvious thing and apply the result that we have, where the vector y here is just the vector y that we're working with all along. But the matrix A, of course, the vector B is just 0. But the matrix A is then the transpose of V, right? Like, if we think that that's what should land here, the transpose of V, because like that's what we would want on this side of the covariance matrix, well, then that would have to come from this matrix A being V prime, the transpose of V. So anyway, so applying all of those principles, we get this equation. Okay. But keep in mind that this is a length n row vector. This is a length n column vector, so that this is effectively the dot product between the two vectors. And so it is just a single random variable. Well, if it is a single random variable, then when we take its covariance, right, to confirm this, you may want to look back at all the technical things that we said about what the covariance is, but you should find that when you take the covariance of just this 1-by-1 matrix or vector of random variables, that it is nothing other than the variance of that random variable. Well, from here, the variance, this is just a well-known fact from mathematical statistics, that the variance of any random variable is always a non-negative real number, and the proof is complete.